Alright, with 3.5 and exponential growth and decay modeling data, basically you have two different formulas, or you have one formula, but the biggest difference is your K value, is it positive or is it negative? Okay, if it's positive, then it's going to be growth and it's going to be growing. If it is negative, then it will be decay. With this, the A sub 0 is your initial amount. Whatever you, like if we're dealing with E is still E as far as our what we have. T is the amount of time that we're dealing with. And then, like I said, your E is just dependent on whatever we have as far as our base or whatever we are multiplying with. So it says the graph shows U.S. population in millions for 5 selected years, 1970 through 2010. In 1970, population was 203.3 million. 2010 grown to 308.7 million. So it says find the exponential growth function that models the data for 1970 through 2010. So first thing we need to know is, what do we have as far as my values are concerned? Well, first off, we have to know what our initial amount is. So our initial population in this case is 203.3. When we deal with the time, so the time was 40 years, and then we ended with, we've got to figure out what our K is, or what our constant value is. So we know that our ending year is at 308.7. So then we're gonna plug it into the formula. It obviously, just by looking at our graph, is growing. Okay, so this will be growth, so our K value should be positive. So whenever we do, we just plug everything in. We take the 308.7, set it equal to 203.3 e to the 40k. Okay, remember that e is just another arbitrary number. That's the perfect number, the natural number rather. Divide both sides by the 203.3. 203.3. Looking at so then I'm going to have the decimal. I'm just going to leave it like this for right now, and then 203.3 equals e to the 40k power. Now, since it's e, I'm going to have to use the natural log. So I'm going to take the natural log of 308.7 divided by 203.3 and set it equal to 40k. So once I will plug this into my calculator, okay, which is going to be about 0.0104, and then so I would plug that in first, then divide by the 40k, or by the 40. So then after I get what's in the box as far as my value, I would leave that in my calculator and then divide by 40. So whenever I do that, my K value would then be equal to 0.417. So then all I'm going to do is basically just take that and plug it into my original formula. So I have to take my initial amount. So if I want to find any year and what value, I'm going to take the 203.3 e to the 0.417 t power. So that way, if at any point, which I'm going to do here in a second on B, is if I want to find any year, so not just within, if I want to know in 2019 what my value is going to be, okay, or when is it going to reach, like on B, when is it going to reach the 335 million? So, but even if I wanted to find like this year, if it continues on this trend, what is, what's the population going to be after that much time? So from there, my mistake, whenever I divided it by the 40, then I got the 0.104. So then my equation, the 4.17 was, whenever I took the natural log, 0.104. My mistake, 0.104. So that's what my K value is. My mistake that I had my numbers backwards. So whenever, like if I want to find whatever the value is whenever it's 200 or 335 million, okay, so like on part B, all I'm going to do to set this thing up for part B is take the 335. Now that I have my K value, then it just becomes the 203.3 e to the 0.0104 t power. Okay, I'll still take the natural, I'll still have to divide by the 203. I'll end up getting 335 divided by 203.3 equal to e to the 0.0104 t power. Okay, I'm still going to turn it into a natural log. So whenever I take the natural log of 335 divided by 203.3, so whenever I do that, I have the natural log of 335 divided by 203.3. I have it's about a half. But then whenever I divide it by, because that's going to be equal to my 0.0104 t, whenever I divide it by that, 0.104, it's going to give me about 48 years. Okay, so just a little bit over 48 years is how long it's going to take. Then the second main formula that is a very important formula as far as Newton's law of cooling. Basically, you heat up any object, and then where if you sit something out, like if you bring soup to a boil, and it is completely, or you take something off the grill or out of the oven, you don't immediately eat it or drink it, whatever you are dealing with. You may have to leave it out for a certain amount of time. Okay, so it's not one of those things. We don't just bring soup to a boil, keep it boiling, take it out of the pot, put it in a bowl, and immediately consume it. Okay, you have to let it cool so then you don't burn your mouth or whatever. So what Newton's law of cooling tells us is that if it sits out, if whatever our object is, it gets heated up, and then we leave it out at a constant temperature, the thermostat set at 75 or 70 degrees, how long is it going to take for, the cake, like in the example, the cake or the soup or whatever we're dealing with, the water, how long is it going to take for it to cool down to a noticeable temperature. You know, like in this case for the cake, you know, you don't want to put the icing on immediately because it's just going to melt the icing or whatever. So with this formula, you have C. C is the constant temperature of whatever the room is. T sub 0 is the initial temperature of the heated object, whatever object you're heating. K is a negative constant that's going to be associated with the cooling object. If you think about it, cooling is going to it's going to decay. You want something to lower in temperature if it's going to cool off. So your K is going to have to be negative. Okay? Hopefully that makes perfect sense. So then you can go from there. So if we want to know, we have a cake removed from an oven, temperature of 210 degrees, okay, and left the cool in a room that's 70 degrees. After 30 minutes, the temperature of the cake is 140 degrees Fahrenheit. So we're going to use the formula, again, like it said right above it, that you do not need to memorize this formula. So I need to know a few things. So I need to know, like for A, I need to know what my initial temperature was. It was 210 degrees. I need to know what my constant temperature was. It's 70 degrees. And then when the time is 30 minutes, okay, so 30 minutes of time, then I want to it was a temperature of 140 degrees. So from there, I'm going to have T equals C plus whatever my initial temperature was minus my constant temperature, and then E to the K times T power. So 140 was my constant, or what my new temperature was. My constant temperature is at 70 degrees, plus my initial, which was 210, minus 70, E, and then K, and then 30. So 140, I can subtract the 70, or subtract 70 from the 40, so I'm at 70 equals. I'm going to kind of do two things at once and subtract those two values and get 140. E to the 30K. Again, I'm trying to solve for K, so I'm going to divide by 140. So I have 1/2 equals E to the 30K power. So from there, turn it into a logarithm. So whenever I do, I'm going to have the natural log of 1/2 equals 30K. So I'm going to divide that by 30, so I'm going to take the natural log of 1/2, or 30, and then divide that by 30 and end up with, so I'll divide that by 30, and my K value is going to be negative 0.0231. Now, I'll use that, so as far as my equation is concerned, I'll go back and plug that in basically to the point where I'll basically plug everything back into my original with the information that I had of T being equal to whatever my constant is, whatever the 210 minus the 70, and then E to the negative power with the T. So then for my So if t is equal to 70 plus 140 e to the negative 0.0231 t, okay, all I'm going to do is for like on B and on C is to use the formula that I have, and like after 40 minutes, what is it? So I'm going to plug in 40 for the time. After, if I want it to be 90 degrees, plug in the 90 for the T and solve from there. So everything is based off of the formula that I have created now for this particular instance. Now, obviously, one thing changes. If it turns from 70 to, we turn up the thermostat from 70 degrees to 75, it's going to completely change everything. Okay, but this is just for this one exact case of the cake being pulled out at a certain temperature and going from there. Last thing then is just expressing an exponential model as base E. Basically what you can do is if I have E, A times a number to the x power, just like what we talked about 2 days ago, that we can turn any exponential into the natural log of my base times whatever that power is. Okay, it's no different than what we did on Wednesday, so that this part here is the same thing we did whenever we factored and we solved from there. Okay, so none of that's going to change. Your A doesn't change, it's just we rewrite our base from a number into a natural number with an exponent of whatever the natural log of my base is times x, or whatever my exponent is. So that doesn't really affect a whole lot of things.